All right, let's start. Today we will learn a new defense mechanism and then mostly focusing on how to avoid that defense. And then the defense is called ASRL, address space layout randomization. So we learned about the defenses, a base and bound check, which is a fundamental defense against the buffer overflow attack, but it's slow. And then we also learned about the two mitigations. One is stack cookie. And then I already know that some of you successfully bypass like stack cookies. Yeah, so it's a very simple defense, but it has a great effect. Yeah, so the challenges I designed are designed for like the leaking stack cookie for you, but in the most cases, like that will never happen. So the implication of the stack cookie is that like to launch the buffer overflow vulnerability, you need to find actually two vulnerabilities. One is buffer overflow, and the other is like the information leak. You need to leak the address space information, or not an address space. And you need to leak the stack cookie value to that. And then we will do the same thing for the address space layout randomization. We need to leak the address information to launch the buffer overflow attack. So the implication is like it's at the bar, another bar, yeah, to raise the bar for like for the successful hacking. And we also learned about the data execution prevention. So that will immediately block like the running of shellcode or that kind of the privilege from the the systems. And then the reason why that was enabled later, around the 2004, although stack cookie was available in 1998, was like that requires a hardware change. And the implication is like for the pure software defense, we can immediately apply that with the compiler tricks. But for the things that requires hardware change, that requires some times to deploy the thing. Yeah. And the defense that we will learn today is like it's called ASRL. It's randomizing the address space, and then it's a pure software defense. So yeah, it can be applied quickly, but you'll be surprised how the world was going. Maybe you guys never know about what's the C language or something. Yeah, because like the ASRL was fully enabled in 2014. Yeah, but before that, even if the idea was so good and then it's quite easy to apply, there are many practical reasons that we cannot apply that for the entire machines. But thankfully, your machines are, I believe, all enabled with the all three defenses. Yeah, so yeah. And let's do a little recap about the stack overflow and then stack buffer overflow and then running the shellcode out of it. So what we do is like after identifying the buffer overflow vulnerability, we fill the buffer, then alter the control data. Specifically, if we can overwrite the return address as a address of the shellcode. Then we jump to here, and then CPU will run it. But to make this attack possible, we need to know where your shellcode is located at the program's memory space. And to do that, either we can generate a core file to find your shellcode from there and then reuse that address, or we can put lots of knobs as a knob sled and then just pick some of the address and then it will work. Yeah. So because like we know that where the stack will be ranged and then pick any kind of address, and then we can have a high chance to hit the big knob sled or something. So in the memory space, your shellcode will be put as like this. And then can you identify where the shellcode is? So if you want to become a top level hacker, yeah, I would like to ask you better to read opcode. Yeah, right. You can see that, right? Yeah, something CD80. So like actually, like it starts at 6A is a push EA, a push 32, 58 is pub EAX, right? And then CD80, and then A9C3 is like moving registers. Yeah, so something like that. So yeah, so it's not that hard. So that sometimes I read the opcode and then, oh, there's a function and there's something, and then like some of the novice hackers that go, oh, Youngjin is genius. No, anyone can do that. Yeah, anyone can do that. Yeah. So I don't think like the hacking is a magic. Like if we study it systematically, then I'm the believer that anyone can hack very well. Yeah. And then I believe it's much easier than algorithm exam or something. So this is your shellcode. And then like because shellcode was a little off, so to align it to the 8-byte or 16-byte, like I just inserted 90, which is an op. Yeah. So if you put this address, then your return address will be this one, then it will run your shellcode. That's the attack that we were doing. So let's think a little about like what is the prerequisite about this successful attack. So attacker need to know which address to jump or run or something like that. So we can inject the shellcode on the stack, then we need to know the address of the shellcode in the stack. Or we learned about how we can defeat the data execution prevention. In that case, we return to libc library functions. And for that case, we also need to know where the functions are located. Yeah. And then VMCTF1 server, I intentionally changed the configuration to not randomize any kind of address, yeah, for the teaching purpose. But in the rest of the set of the challenges, we will not use VMCTF1 anymore. Yeah. So ASRL challenges will be hosted in VMCTF3, and then week 5, 6, 7 will be hosted in the VMCTF2, which I enabled full security on that. So what we are doing is like starting from 1990s and then going up and up and up, and then like that week 5, you will learn about like the playing with the latest machine techniques. Yeah. So you will have much more fun and then have much more confidence about that. So the defense is very simple. So attackers need to know the address, then let's randomize it. Yeah, that's it. Yeah. In that case, attackers may not know where to jump. They'll know where the exec function is, where system function is, where the shellcode is, then we can win. That's the logic. And let me give a little history about the ASRL before I explain the details. So the history of the ASRL is like you know that the Linux has this penguin named as Tux as their iconic thing. Yeah. So Linux is penguin, and then there's a team called PAX. I don't know what each character stands for, but that group is like the open source group that mainly develops something for enhancing the security of the Linux system. And their icon is something like this. Yeah, defend, but I don't know why they do have this. Maybe they're killing the attackers. Yeah, right. Yeah. So not the original Linux, because like, do you know how the Linux evolves? So there's a head of the maintainer called whose name is Linus Torvalds, and then there are 12 or 13 maintainers, and then there are committers. So like anyone can commit and push the code to Linux, and then each maintainer will evaluate all the lines of the code, and then if they like it, and then it will go up for the Linus Torvalds, and then only the code that Torvalds approves can get into Linux kernel. And then do you also know that Linus Torvalds live in Poland? Yeah. Yeah. I was surprised, and then one student told me that he went to high school and he saw the students whose last name is Torvalds, and then he thought that oh, maybe, but that student was using Mac, so like he was think that like oh, that's not the Torvalds way, but the lesson is like even Torvalds' daughter, yeah, don't want to use Linux. That's a funny thing, but I like Linux. So the reason why I explained about that is like getting into the mainline Linux kernel is very difficult, and then it has to be proven to not affect on the compatibility and the reliability and performance of the system. And then only the best technology can get into the Linux kernel. So that at that time, it was kind of new, so that cannot be get into Linux kernel. And then that was happened in the 2005. So there are 3 years of like the proving the technology kind of the period. Yeah, so that's the thing. But the OpenBSD is different. OpenBSD is like it started with the BSD is called the Berkeley Software Development Distribution or something. So University of California, Berkeley, there are some of the operating system makers. They developed the new operating system, and then OpenBSD is the open source version of that. And then they do not have that kind of strict management or something. So they move fast. So they adopted the ASRL in 2003. And then because the technique is good, and then approved by the Linux kernel community. Yeah. And then what happens is like all the proprietary operating system designers would like to copy and paste their new good, great technologies. So the Windows follows in Windows Vista in 2007. Yeah. And then iOS, Apple, yeah, they implemented, yeah, it's quite interesting. Even macOS did not implement that one, but the iOS implemented it like fully first, and then later macOS, and then Android. And the full history is something like this. So in 2005, Linux kernel 2.6.12, they applied ASRL to the user space. And the user space here means that the program that you run and write. So mostly these are in the user space. And then the opposite term of the user space is kernel space. So it's the internal of the operating system. So at the first time, yeah, Linux apply the ASRL to the user space because it is good. Windows move forward with a big step. They apply that to the both kernel and user space. And then OS 10 applied to the user space in 2008-ish. And then 2011, iOS applied that, Android applied that, and then moves to the kernel too. And then Linux kernel applied at the end. And then you can also see that how Linux kernel is conservative for the adopting the technology. Yeah. So what I want to tell is like this technique is proven to be beneficial to security, and then very reliable, and then work with the other programs. But the main reason of like that takes a lot of time to apply this technology is that there are a lot of programmers, they assumes that they will have a fixed address space. And then if they change the underlying operating system to support this, then many programs were broken. And then especially for some of the games, yeah, they would like to get the performance as maximum from the CPU or something. Yeah. And then have you ever seen John Carmack's code in Doom for running the Newton method? Yeah. So I want to show that code. Yeah, because some of the students have not seen that. So that code is measured. And then so that is not directly related to the ASRL, but I want to demonstrate that as a like example of like some hackish way what the programmers are doing. And then that some other cases are affecting on the address space kind of thing. So let me show you that. So I need to accept this. And I need to share the screen. So do you know what is Newton method? Let's get the derivative and then like the calculating something, yeah. So that definitely, so it's something like what it does is like it calculates the inverse square root, something like this, yeah, square root x over 1, yeah, and then that definitely requires a floating point operation, operating with the double or float the data. But the adding and multiplication of the floating point number is much more slower than the integer numbers. Yeah. And then what they did is something like this. So they got float number. They want to get the square root of that number over 1. Yeah. And then This is the floating point number. This is the floating point number, but they cast floating point number as a long pointer. So it is a pointer cast. What that means is like if we cast the double into long, it will convert the floating point number to the integer. But in this case, it will leave the representation of the floating point number in the memory and then just interpret that as a long number. So if you try this, you will see that that is not the same number at all. Yeah. And then they do something like this. I know this is not that good for the education, but yeah, just read up to this part. Yeah. So one shift operation and then minus. It can be finished in 2 cycles. But if you run the real Newton method, it will take like a 70 or 80 cycles. So they optimized it with this way. And then if you're curious about the details of the thing, it's quite worth reading. Yeah. So there's a representation of the thing, and then this actually means like the applying logarithm in the floating point number, and then this is something for the Newton method. Yeah. So the implication is like that is like the to harness all the performance that the CPU can do. Yeah, even in the limited case, most of the programmers they would like to use hack. So that's a different kind of hack we are learning it here, but like it's somewhat performance hack. That there are a lot of hacks like that, and then assuming that there's a fixed address space or something that may be broken when we change the underlying operating systems. So that's why the adopting of the ASRL took so long. And then the reason why open source softwares can apply it first is like a lot of proprietary softwares are doing this kind of thing. Yeah. And let's continue. And then, so Linux apply the kernel space ASRL. What that means is like for the user space, whenever you run the program, if you run the program again, the entire address space will be different, randomized at each time of the execution. And for the kernel space, it randomized the kernel addresses at the boot time. So if you turn off and turn on the computer again, then your kernel address space will be randomized. Yeah. And then this guy, his name is Kees Cook. Yeah, Kees Cook or something. Yeah. He's a maintainer of all sort of the kernel security. Yeah. And then he ran a fuzzer for like a syscaller for finding the security vulnerabilities of the Linux kernel, and also applies the kernel ASRL. So he was a supporter for the kernel ASRL, and then all the maintainers do not wish to include that, but his stubborn the thoughts, yeah, made our world more secure. Yeah. And then he also lives in Portland. Yeah. And then I believe he belongs to Google, but he's a free spirit kind of thing. So like Google just pay money while like he's keeping maintaining the Linux kernel. Maybe they ask for there's no evidence, but maybe they ask for like applying something for Android, because Android uses a Linux kernel or something. Yeah, I don't know, but so super great hackers are free spirits like that. And then this is 1003 KEC. Yeah, he sometimes come down here and then gave a talk. Yeah, so we invited him at OSUSEC in 2019. Yeah, so that was quite fun moment. And then he demonstrated like how we can exploit the kernel vulnerability. Yeah, so that was a fun moment. Yeah, maybe we should invite him again. Right. So that's the little historical and then funny stories about the ASRL. Any questions before we get into the details of the ASRL? And let's move forward. So ASRL looks like this. So in the program's memory space, we allocate stack. So you have seen the stack address space. It starts at the FFFF, it's some E000 and then FFFF something. And then library codes are somewhere like the B7 something. And then the program code space is always like a 8040 something. Yeah, you have seen those kind of addresses. So that's the world before applying ASRL. So this is the normal way. But after we had the ASRL in the kernel, and then every time you execute the program, so you can regard this like a red line as a one execution. And then if you run the program again, then actually the kernel shuffles the base address of each region. So right now stack is not randomized at all, but the stack is also randomized. Yeah. So you can think it as like there are 4 different regions, and then they are shuffled, and at each time you execute the program. And then if you fetch week 4 challenges in VMCTF3 server, you will see that a program called the ASRL check, you can run that on the server. So like I placed that to like see how it changes. So in the program, I printed the stack address, heap address, libc address, and then you can see that the addresses are changing at each time of the execution. Because internally it runs this program for 5 times, yeah, and then keep printing the addresses, and then you will see that the addresses are randomized. Yeah. So this is how we can easily defeat attackers because they will never know those kind of addresses. But the important thing is that whenever there is a randomness, we need to think about how strong that random is. So for example, if we just flip the coin, if we make a random guess, we will have a 50% chance to make a correct guess. If we flip 2 coins, then 25%, something like that. So we call that like how many bits, how many of like the uncertainty in the randomness. And then we can measure that thanks to the Cloud Shannon, who developed the entire information theory. He used the physical term entropy to measure that kind of the randomness, strength of the randomness. And then, so for the 32-bit machine, so for the stack addresses, so you can take a look at the kernel code to how do they randomize a thing. And if you analyze that, you will figure out that their entropy is 19 bits. And that means 1/2 to the 19. You can make a successful guess, even if you make a random guess. So the chance of attacker, they can make a successful random guess is 1/500,000. And for the heap addresses, although stack addresses, there are around the 4 digits are changing in the hexadecimal, and then you can regard the 1 digit in hexadecimal as a 4 bits, because it can represent the 16 cases. And then for the heap addresses, 3 digits are changing, but always it's like the 7, 8, 9, like not about the low number kind of thing. So the heap space is randomized as the 1/8,000. And then for the library space, although they change it 3 digits, you will see that it will be the top digit is either D or E. So they don't have like a full 12-bit randomization or something, so that their entropy is just 8 bits. So if you make a 1 guess, run the program more than 512 times, there is a chance you can win. Yeah. So in 32-bit machines, because the address bits are quite limited, so that we could not have like the strong random, we could not insert the strong randomness. We could not have strong entropy for the randomization. But in 64-bit, we have much longer pointers. And then like for the most of the machine right now, we are using 48 bits address space. So we have 16 more bits in the address, so we can add more entropy for that. And then the recent version of CPUs, starting from, I believe, Intel's 7th generation or something, they do support the 57 bits address space. Yeah. So although like most of the operating system do not apply that, because like most of us do not need 256 terabyte of memory. Yeah. So because 48 bits can support that much memory, and then like the 57 bits are like the much more, like the sum of 16 petabyte or something. Yeah. So to be future-proof, like they designed the CPU like that, but I don't believe like most of the desktop machines will use that soon. Yeah, because there are some of the performance issues about that. But even for the 48-bit address space in the 64-bit computers, we can insert 30 bits entropy. Then your random guess chance is like 1/1 billion. Yeah. Then better to purchase Powerball. And then I heard that the recent Powerball won by like a Seattle or something near here. Yeah. Yeah. So in one of the challenge, I created you need to do the brute force, and then please don't try that on the stack. Yeah, if you want to do that, better to go to the grocery store to get some of the lottery tickets. Yeah. And then for heap, they do have 28 bits, 28 bits, and then even for Windows, the worst entropy with the 64-bit computers, their successful chances like 1/500,000. Yeah. So practically, if we apply ASRL well, then like we could have like this much of a guarantee that the attackers cannot make a random guess and defeat the attack. Yeah. So that this is the 64-bit case, and then you will see that lots of digits are changing. Yeah. Even if I run the same cat program again and again. Yeah. Any questions? So the implication is, even if you get the address from the core file, on the next execution, your address will be randomized. So that address is invalid. Yeah, that's the implication. And then I emphasize that there are always a security and performance, security, usability, that kind of the trade-off. Then the next is talking about the overhead. Yeah. So if we randomize the address space, so if you take a look at the disassembly for the prior challenges, so for the calling printf for the sum to string, you will see that in the disassembly, it mentions about specific address, push 0x8049 something as a string address. So that we can use that kind of fixed address if the ASRL is disabled. But if it is enabled, we need to access all the data relative to the code address. The reason is, in ASRL, we do not shuffle all the address. So there's a program code and data, we shuffle them together. So the relative distance between the code and the data will be fixed, but the actual address will be totally different. So to run this kind of thing, compiler need to generate the code by calculating the relative distance from the current instruction pointer to the data, and then load that address accordingly. So how that is done in 64-bit is, so thanks to AMD 64, they designed instruction very well. What that means is that we can access over RIP, which is an instruction pointer. So this load expected address instruction, what it will do is like it will set RDI as a RIP plus this number. Yeah. So we can do operation on instruction pointer and then get the address. So if we know the relative distance like this, then we can use this instruction, yeah, to get the location. But the reason why I thank to AMD 64 is like the x86 32-bit, they do not allow any kind of operation over instruction pointer. You can never use EIP as a target or source register in any kind of assembly. Then my question here is that we must know the code address and then do the relative offset calculation. Then how can you get the value of the EIP? Can you answer that? Yeah.
Then they just store the value somewhere. They're gonna store the absolute value.
So how can you store the current instruction pointer? So you cannot use EIP register in move, LEA, any kind of the operation. Yes. That's right. Yeah. So how we do that is call +5 here means that we will call right next instruction and then pop EBX. Did you get it? The semantic of the call instruction is that it will jump to the right next instruction, but it will store the address of the right next instruction to the stack as a return address. That's the semantic of the call. So in 32-bit, to do this kind of thing, so you will see that the weird disassembly in this kind of the, in the challenge set of the week 4 for ASRL. So what it will do is like call to the right next instruction and pop EBX, then it will get the instruction address of this one into EBX. This is a hack. Yeah. And then add the offset. Then we can get the access the instruction pointer. Yeah. So the lesson here is that there's nothing impossible. Yeah. So if we think harder, then we can do this kind of thing. But the problem is that this instruction is quite neat. So it's just a one adding instruction. So it can be finished in one cycle. But if we do call pop add, it will screw up all the branch predictors and then other stuff. So it's very slow. That's why we have a less than 1% overhead in 64-bit for the ASRL, but we could have like a much more, around 3%, even much more is 3%. Yeah, overhead in 32-bit. Yeah. Any questions? Yes. So it could be different, but conceptually, ASRL does not have like any kind of restrictions. Yeah. So the only restriction to Intel CPU is that we cannot get EIP, so that we need to do something like that. But in ARM, it's quite free to get they do have like the instructions that are moving over IP. Yeah. So it's somewhat similar to the AMD 64. Yeah. So it's somewhat architecture dependent if they disallow accessing of the IP. Yeah. Any other questions? Then let's move forward. And how can we bypass ASRL? So the first naive way is a brute force attack. So what you can do is, if you know where the buffer overflow vulnerability is, crash the program. Then it will give the snapshot of all the address space as a core file. And then you can find your shellcode address or some other function address or a library space address or any kind of address. And then fix that address. If that is shellcode or if that is system or something like that, fix that address and run that again and again. Then eventually it will match it. It will be matched because there's a limited entropy. But with this table in 32-bit, which address do you want to try for this brute force attack? Library. Yeah. Even if I show this table, I've seen a lot of students trying to run brute force attack on stack because they know, oh, I know how to put the shellcode on the stack and run it. Yeah, please don't do that. Yeah. So for ASRL 6, that challenge requires you to launch the brute force attack. In that case, please use all the addresses in the library space. So the most difficult part for the students were, so they can find the system address. But sometimes they find bin sh address from the stack. then 2 addresses need to be matched. So that means 19 plus 8, 2 to the 27, is actually getting more harder, 128 million times. Yeah. So in the ASRL 6 challenge, find system address and also find BNSH address or execBE or BNSH address all in the library space. Then your chance will be exactly 1/512. Yeah. And then if someone asks like oh, my exploit does not work, and then they use like a different address, then I will just reply with this table. Yeah. Then let's delve into a little bit about the challenges. So in BMCTF1 server, you will have 6 challenges from ASRL 1 to 6, and then you can learn it step by step. So the first challenge, kindly give you the address of the buffer. So what you need to do is, so you can put the address, you can put your shellcode in your buffer. And then you know the address. So programmatically, you need to read this address in your Pontool script, and then put that address as a return address. Yeah. So that's the challenge. And then you can easily read these things as a read line or something, and then split it, and then convert this hexadecimal number to the integer. Yeah. And then use P32. Yeah. These are the things you need to do. Yeah. So the implication of this one is like if there's an information leak about the buffer address or a library address or something, then you can easily defeat ASRL. And so this is a very easy case. The challenge explicitly let you know about where your buffer is. But in some cases, you can leak the address, but that address would not be the address of system or address of execBE. But you don't have to worry, because the characteristics of the user space ASRL applied right now is they just shuffle the region of the memory. So for a specific region, all the relative offsets fixed, because we don't change the code. So think about it. We have a libc.so. This is a binary program. We just load it in the memory. We do not shuffle internally. What we do is like just shuffle in the memory space like this. So all the relative offset is the same within the region. Yeah. So to give a better idea, so there's another program, ASRL check 2. You can run it too. Yeah. And then when I run the program, all the stack addresses for the variable 1, variable 2, variable 3, their addresses are something like this. But you will see that the distance between the variable 3 to variable 2 is 4 byte. So F5FC plus 4 is a 600. And then this plus 4, this plus 8 would be 608, right? So difference is 4, and then difference between 1 and 2 is 8. In the next execution, difference between this 3 and 2, 4, 2 and 1, 8. On the third execution, that's the same. And that will be the same for each area. So if you calculate the difference between variable 2 to the heap, variable 2 to the libc, that'll be totally different. But within the same area, if you calculate the relative offset between the variables object in the memory, then you will see that all the things are fixed. So what that means is that, so for the library space, this is very important. So suppose you leaked address of the printf. Maybe you think that printf is not useful for the exploitation. You will change the mind in week 6, because we will learn about another attack using printf. Yeah, but for now, printf may be like useless for the exploitation. But you can calculate the distance between the printf and system. And then the distance is like that. If we subtract this number 59600 from the printf, then we can get the address of the system. And then every time I run it, that distance will never be changing. So what that means is that, suppose you leak the printf address. And then using GDB, you can open libc.so. That's a fixed binary file. Get the offset between the printf and the system, subtract that. Then you can get the address of the system in the library space. That's how we can defeat ASRL. So for the ASRL2, that challenge will leak some of the pointers like this. And then you will realize that some of the address starting with BF is for stack, and then some of the addresses for B7 is in the library space. Yeah, you will see that after running the ASRL check 1, ASRL check 2, there's some of the fixed part of the addresses. And in ASRL 2, you need to distinguish which addresses are belong to stack or belong to library space, and then fix one address, and then calculate the offset to exactly know about where your target function or a string or useful things are located at. Yeah. And then I will demonstrate some of the demo for like how to solve them. Yeah, at the end. So like, please don't worry about like if you cannot understand what's going on. So the important thing is like relative addresses are fixed. So we will exploit that to calculate the exact address. So how to pound the ASRL2 is that they leak the addresses. The ASRL2 and 3 are somewhat similar, but the ASRL3 is much easier technically, conceptually, but it has a little bit more coding stuff is required for the Python script. So that's why I said that ASR3 is a little difficult one. And how you can solve it is like you need to leak any kind of a library address. So that could be printf or some other address. And then you can open the library file. So if you run LDD, then it will kindly let you know where the libc program is. But please ignore this address. This address will be randomized every time when you execute the program. So that we don't care about the address for now. So if you open the GDB with that binary program, you can print the address of the system, offset of the system, offset of the printf, offset of the puts, any kind of function. And then if you calculate the distance between these kind of functions, that will be fixed. So at the runtime, we leak one library address. And then if we know that which part of the library object it points to, then we can calculate some offset and then adding the system offset. So we can get the address of the system with a little bit of calculation. So, and then to apply ASRL correctly, we need to apply ASRL to all the regions. That means the program's code and then program's library, stack, heap, and then future mmap. So mmap is a memory mapping functionality in the Linux kernel. So every time we create a new address space, the address space need to be randomized. Yeah, the thing. But sometimes still, it happens to be like the code and data address are not randomized. This is because there still has a lot of compatibility issues. But I believe that any kind of program written after 2014 would not do so. If somebody does so, then you can report that as like a potential vulnerability. Yeah, and then blame the developer about that.
Yeah. So the best practice is never do that kind of thing. And then we should follow the guideline. And then ASRL is the standard technique. So the developers must be aware that their address spaces are not fixed. Yeah. So to randomize the code and data, it is so-called the position independent executable. So in the latest distribution of the Linux operating system, they enable the PIE as a default. So here's the example of the PIE and non-PIE. So for the non-PIE binary, /bin cat in vmctf3, because this is the old distribution. Yeah. So they say this file is an executable file, and then entry point address is fixed like 8049 something. But for the binary file that is enabled with the position independent executable, they say dynamic shared object file, even if this is just a binary file. This is an executable file, but they say it's a shared object file because the library files are the only one that can be placed anywhere before ASRL is born. Yeah, they just reuse the existing scheme. And then their entry point address is not about the 80 something. It's like 1B5 and 19. That's the offset starting from 0. Yeah. So to check if the binary program is a position independent or not, so you can take a look at this kind of the executable or shared object. So in this case, all the addresses will be randomized. So we have a separate set of the assignments hosted in the vmctf3 server. And to describe each challenges, ASRL1 kindly leaks the buffer address for you, yeah, so that you can take advantage of that. And then ASRL2, it leaks some of the stack addresses. And you can figure out what is the buffer address or what is the some other addresses, and then you can do the relative addressing to get the buffer address. So one hint is that run the program many times with GDB or like a core file. Try to identify some of the distance between the start of the buffer to the one of the value that has been leaked. Then you will see that some of the fixed offset, and then later from that address subtract the offset, you can get the buffer address. And then ASR3, this is actually the conceptually easier than ASRL2 because you can leak as many bytes as you want, but technically you need to convert the binary stream into the integer value and then calculate all the stuff. Yeah, and then you might need to use like a lot of U32 or something like that. And then I will demonstrate how you can do that. And for ASRL4, so ASRL1, 2, 3 is all about you can put the shellcode in your buffer and then exploit that. But for ASRL4, you need to use the library space. So the program kindly leaks that tells you about like where the printf function is. Then with the offsetting thing, you can get the address of the system and then, yeah, pound the program. And for ASRL5, there's a no leak. You need to call some of the function to leak the addresses. So there is a buffer overflow vulnerability, and then the program is not position independent executable. So code addresses are fixed. So you can reuse some of the code in the binary program. Then you can leak the data. And then in this case, you have only one chance to launch the buffer overflow vulnerability. But technically, you can have an infinite chance of launch the buffer overflow vulnerability. How you can do that is, so now some of you know that like with the DEP technique, yeah, that DEP3 or DEP2, DEP3, we can chain some return addresses to call multiple functions. So how we can do that is like set the return address to the calling some of the function, when they return, we set the next return address as an input function. Then it will return back to the input function, get our input again. And then if we set the return address as an input function again, then there's a loop. So that you can create the loop of like a buffer overflow vulnerability. So even if there's only one buffer overflow vulnerability, one chance, you can make it as an infinite chance, and then leak the old address and kill the program. That's the ASRL5. And then ASRL6 is about the brute force attack. As far as I know, there's no other ways to solve that. Yeah. And then please try that with the library space. Then you can win. So these assignments are hosted in VMCTF3, and the due date is 2 weeks later or something. Yeah. So you can have plenty of time to do that. Yeah. Any questions before I start the demo for some challenges? If there's no question, then I would like to tell a little more thing about the ASRL. So I told you that we are randomizing the area of the program. But we can actually shuffle all the instructions or all the function addresses. We can do that. In that case, this kind of the offsetting attack will never work. But can you guess why we cannot do that? So there is an overhead, but it's different overhead. So have you heard about the concept of copy on write? So suppose you have a Google Chrome, and then if you open a lot of tabs, each tab is a single process. And then Google Chrome binary program is 300 megabytes, and then it will load lots of library programs. So one process will take up around 1 gigabyte of memory. And then how many gigabytes of memory you have in your laptop? 16, maybe 32. But if you open 32 tabs, it will use all 32 gigabytes of memory. Yeah, but that's not true. So we can even open 100 tabs, and the system works reliably. And then how that works is for the code data, they are not writable. They will not be changing. So how we do is whenever we create a new process, it does not allocate the new memory space. So physically, we have only one copy of the Chrome binary library, and then virtually we link them to the same address physically. So basically, we share all the code across all the processes. So when you run Google Chrome and then opening unlimited of the tabs, then their code will have only one copy. And then data also has only one copy, but whenever one process write on it, then operating system make it as read only, but they flag it as it could be changeable. And then after operating system detects that, then only for that page, it will copy. So it is so-called copy on write. Yeah. That's the concept of the system design, that we can share a bunch of the memory space so we can reduce the memory footprint. Yeah. Then what if we shuffle the content of the code every time we run the program? We cannot share that kind of the library program. So yeah, that means if we open the 80 tabs, then it literally requires 80 times more memory. Yeah. So there are a lot of academic papers from prestigious school. I can show that. Wait a second. So I need to share that origin too. So there's a paper called Address Space Layout Permutation. Yeah, academic researchers have been doing this kind of research, and then some of the Google engineers participated in that. Yeah, so high-profile persons that do the research, but I regard this work is purely academic, never be adopted in reality. Yeah, so I personally don't like this kind of research. Yeah, but the idea is good. And then what they did is actually like so whenever they load the library, they shuffle the location of each function. Yeah. That will totally break copy and write. So how I regard is that these researchers don't know about that there's a copy and write on the operating systems. Maybe it could be useful for like a single process operating system, but not about the generic purpose operating systems at all. And then, so the reason why I'm showing this is like that there's a battle between the hackers and the researchers. So the hackers sometimes think that the academic papers are total BS because like they design something like that that's not useful at all. But the academic researchers think that the hackers are BS because like they are not fundamental and then they are not generating systematic knowledge or something. And then I do both sides, so I can judge them. And then there's another paper. Yeah. Binary string. Yeah. So what they are doing is then not just for the function, shuffle the instruction orders. So that there are some of the instructions that does not depend, that if it's like a EAX, ECX, EDX, ESI, then we can shuffle that, right? Yeah. So do that kind of thing. This can never be adopted in the generic purpose systems. Copy and write, right? Then there's another crazy work. So this conference, OSDI, this is the most prestigious operating system conference that one of my dream venue for presenting my research. I haven't done that yet, but I can easily say this paper, this work will never be adopted. Yeah. So I don't care about the authority. So these are like great researchers. I like Jun Fang. Yeah, his work is awesome. Other works, not this one. Yeah, yeah. And then the reason is what they did was, so they say re-randomization. So that you will realize after launching the attack to the ASRL, then with the one information leak, you can know about all the address space and then attack. So what they want to do is, do they have a diagram or something? So they change the program like this, and then what they are doing is, so they shuffle the entire layout in every 50 milliseconds. Can you guess why 50 milliseconds? Definitely, if it is too fast, then the CPU is just shuffling and then not moving forward. Yeah, but why 50 milliseconds?
When the scheduler takes control.
No, scheduler is less than 1 millisecond. Or yeah, if scheduler takes 50 milliseconds, Linux topos will not approve that. That's why Linux uses O1 scheduler. Reliable, yeah, fast scheduler. Yeah. And one hint is that this mechanism is to defeat remote attackers. That's right. So to launch the successful attack, yeah, so we need to leak the address and then use the address. So if the network runs with time 30 millisecond, 30 millisecond, then 60 millisecond. So after we learn the address, use that, then address has been changed, so they can defeat the attack. Yeah. But what they did is that for every process to get the better performance, they need to dedicate one CPU core just for shuffling, even for the 50 millisecond thing. And another thing is that shuffling breaks the code sharing. Yeah. So I don't believe like that this work can be adopted into any kind of the real general purpose systems. Yeah. Then next is about my paper. I know all the problem. Efficient and scalable cause randomization. Yeah. So I want to teach the security community that, oh, you should learn about the operating system design. And then when we design the security techniques, we shouldn't break the underlying operating system design. I'm here. Oregon State University is great, right? Yeah. So what we did was so where's the diagram? So we tried to share all the code region, and then whenever there is a single crash in the entire system, we randomize the layout. The reason is we believe that there is no way to attacker can make a one-shot guess because the entropy is quite high. Our entropy is like a 32-bit. Yeah, they cannot make a one-shot guess. And then if they would like to leak the address via side channel attack or something, that might require a crash. Yeah. And then if anything crashes, then we randomize the entire address, but in the library space physically. Yeah. So like we enable the copy on write sharing, and then enable the re-randomization of the ASRL. Yeah. But the unfortunate thing is like I also believe like this design is quite sophisticated. Nobody will use it. Yeah, I'm fair, even for my paper. Yeah. Any questions about this kind of the work? So that there are a battle between the academic researchers and the hackers, and then whenever they do something, I will break it. Then I play on the both side. Yeah. And then another work of mine is like the DRK attack. So that the reason why the name of the attack is DRK is like one of my PhD co-advisor is my classmate, and like he's a genius. So like he graduated fast, and then like came as a professor at the Georgia Tech, and then he co-advised my thesis, and then as a homage to him, like his name is Taesu Kim, so it's a Dr. Kim attack. Yeah. So I tried to fit some of the name like DRK. Yeah. So what I did is like there's no paper. Yeah. I exploited the bug in CPU to break the kernel ASRL with the 100% guarantee. Yeah. So like you can read about these kind of things. Yeah. Maybe later I can present this in the class about telling you about the details of that. Yeah, it's quite a black magic. Yeah. So even if there's no information leak, we can successfully get the kernel address correctly. And then this is published in both sides of the ACM-CCS, which is the academic conference, and then also Black Hat USA, which is hackers conference. And then I can confidently say that this work can be used in the both side. Yeah. And then in 2018, so I published it in 2016. Some of the hacker in 2018 used this technique to successfully exploit the Windows page table vulnerability. So there is a chance that the 1/256 case for the kernel ASRL. So if they fail it, they see blue screen. So if they launch the attack, then they will fail, blue screen, reboot, then like they cannot have a good chance to successfully exploit that. And then they use this technique to make the exploit 100% successful. So I can confidently say this is something academic and also something very practical. Yeah. Maybe I bragged about myself too much. Any questions? Okay, then if there's no more question, then let's go for the demonstration for solving some challenges. Yeah. So your servers will be VMCTF3. So please send me the direct message if you cannot log into the VMCTF3. So I write a script to put all the public key, same public key to each of the server. So please let me know if you cannot get in, so I can fix that. So by running fetch week 4, you can get all the challenges. So we'll just remove it, fetch week 4, then you can get all the challenges. And then in the week 4 directory, you will have ASRL check. And then if you run ASRL check 1 again and again, you are seeing that the addresses are changing. Yeah. So you can see that the stack address starts with the BF something, but these addresses are changing. Heap address always start 9 something, and then some of the 3 digits are changing. For the libc address, it always starts with the B7E or B7D, and then changing rest of the part. Yeah, that's why it only has 9 bits of entropy. Yeah. So the library space is the weakest part that you can attack. And then ASRL check 2. Yeah. So there's an error. So please ignore the variable 3. Yeah. So the distance between the variable 1 and variable 2 will be 8 byte. 8 byte. And then not 8 byte, it's actually 12 bytes. Yeah. Yeah. I forgot how to calculate about the arithmetic after I make the code in computers. Yeah. Better to do all the calculations in the computers. Yeah. So important thing here is that for the heap objects, yeah, the distance between the heap 2, heap 3 are all 16 bytes. And then that will never be changing no matter how the operating system randomize the base addresses. And then same thing for the printf. So it calculates the distance between the printf and puts, printf and system. So anytime we execute this, then we can have a system address located here. And then how you can calculate back is, so suppose you know the address of the printf. Then you can get the libc binary at here. Open that with GDB. Printf and system, quit. Calculate the distance. And this is the value. should be string. Sorry about that. Yeah, in decimal number, the distance is 59600. Right? So let's get back. So suppose we have a printf address like this. This was the distance. And then let's get the hexadecimal number. That's B7E11DB0. And that's the system address. And then if you cannot believe it, then what you can do is GDB to any kind of program, break and main, run it. And at runtime, GDB can find where the function is. This is the printf address, and then this is the system address. Then what I will do is printf address minus system address 59600. Yeah. So the important thing is relative offset will never be changing. That's the principles of the copy and write and code sharing, thanks to the operating system design as an hacker. Yeah. So we can exploit that to get the exact address of the system. Right. That's the thing. Any questions about the ASRL in the systems? Nope. Right, that's good. And then I will demonstrate another case. What is that? So this is the read ELF for the BNSH on the system. It says share the object file. So that means the code area will be randomized too. And then bin cap executable file. The code address will not be randomized. So how it is different is, so I will start with the GDB bin cat. If you run start I, no? Good. Yeah. Thank you. Yeah. So in that case, you can see that the address is like the 8049. And then, this is weird. Yeah. So the important thing is like the you can see that it starts at the like the 80 something. But for the BNSH. What? This is a 32-bit kernel. How can you have this kind of address? This is very weird. Yeah, maybe like this is just a GDB thing, but the important thing is like that every time you execute the program, the address will be changing. Yeah, you will see that. This is weird. But the important thing is like the address is not the 8048 something. Yeah, so it can be randomized again and again. And then for debugging purpose, if you run the program with GDB, GDB tries to fix some of the randomized addresses. Yeah. So like the actual execution environment could be different. So please keep that all the address can be randomized. So don't trust what GDB says. Trust on like what you learned from the conceptually, and then trust what you leaked from the program. And then I will demonstrate how you can solve ASRL2. Then I believe like you can solve the rest of the challenges all. Yeah. And then to do that, let me launch ASRL2 with GDB. Yeah. So from the input function, So we can identify where the buffer is from the argument of the read function. So that's actually EBP minus 88. So to get that, I will set the breakpoint at here and then read about the EAX. So our buffer address is this one. Yeah. And then the program leaked these addresses, right? So let me do this again. So if you run ASR2, the program will leak these kind of addresses for you. And then you need to calculate exact buffer address from this kind of leak. And then how you can do that is attach GDB, break right after you can know about the buffer address from the disassembly, and then run it. So the buffer address is this one. So I will copy this. Then the program output is these one. Yeah. And then what I will do is I will copy and paste these as a string as S, and then buffer address as this one. So we have a buffer address and then this kind of string. So if we split it like this, then we can get this. And then I will just get that all the hexadecimal numbers. And then or right 0, 1, 2, 3, 4, 5, 6, 7. Yeah. Yeah. So I will just remove this nil. This is not in the integer format. So now it becomes 0. And then what I will do is I will calculate the distance between the buffer address and then each of these addresses. So should be a string. So this is the distance. Yeah. And then I will do this again because this is a single instance. So I will do this again, but if we can see any kind of fixed value, then by taking that value, subtracting that value, we can get the buffer address. So go to the GDB again. Break that input function, run it again. This is our new buffer address. And then this is our new array, right? To get to the Python again. This is S2, buffer 2 is this one. So first buffer and the second buffer addresses are different, right? And then first leaked address and the second leaked addresses are different. So this is the value that we calculated for the first execution. And then I will do the same thing for the second execution. Underscore ARL will store that. Then for seventh element, we will convert that as a 0 for this nil. And then I will do the same thing. Oh, so right now, so I didn't do any kind of calculation for the buffer address, but what I will do is like I will subtract buffer address for each of the element in the first execution values and then second execution values. So I just converted like a leaked values as an integer. Yeah, so I will subtract the buffer address for each element of the array 2. And then underscore array 3 will be from the underscore and then subtract b2. Do you see any kind of fixed value? Yeah. Second value minus 136 is the buffer address. Yeah. Right? And then let's verify our hypothesis. Run it. Second value, right? This is the value that I get. Same value, right? This is how you can get the buffer address from the leak. And then what you can do is like, you know that, so you know the buffer address and then Stack Overflow shellcode 32 that requires you to put the shellcode in it and then jump it. Yeah, you can do the same thing after you know the buffer address correctly. And then I would like to introduce another command called pawn exec. So it actually describes the program, summarizes the program about their security features. So there's a no stack canary, and then DEP is not enabled, it's not a PIE binary, and then RWX segments means that the stack is executable. Yeah. So in that case, you can put the shellcode on the stack and run it. So it's just a one step forward than the Stack Overflow SC32, because after you know where the buffer is, the challenge is actually the same. Yeah. Any questions? All right, then I believe you all are ready to battle with the challenges. Yeah. So please work on that, and then Lucas and myself will assist you whenever you have questions.